Okay, so welcome again to the continuation of the session. Here we have Matthew Amy. We'll be talking about symbolic representation of quantum computations. Please.
Awesome. Thanks for the introduction, and thanks for the invitation to speak here at the Algebraic Structures and Quantum Computation Workshop. I've never been to UBC, despite actually being at Simon Fraser. So this is a fun opportunity for me. Right, and what I'm going to be talking about today is kind of a little bit of my pet project to a certain extent for the past few years that I've been working on, unfortunately, very slowly. But yeah, it's kind of across a couple of different publications at this point. Okay, so what is this talk about? Yeah, you can see the title there. So this talk is really about how can computers, and also humans, but specifically computers, express, reason about, and understand quantum computations. Right, and we want computers to be able to understand and reason about quantum computations so that they can do things like optimize quantum circuits, right, or verify quantum computations. And humans are very good at this kind of reasoning, right? But computers are not always the best at reasoning about quantum circuits, for example. Being able to find the next optimization that reduces your T count by 90%, something like that. Okay. So how do we typically represent quantum computations? Specifically representing quantum computations in computers, right? Using programming languages and stuff like that. The standard representations are really kind of based around composing linear operators. So we have things like circuits, right? Circuits are a classic representation of quantum computations that we use in computers sometimes to represent what a quantum program is, right? And circuits are really just a composition, a sequential composition of unitary matrices. Sometimes you add measurements, but it's a composition of matrices. Okay. And then quantum programming languages kind of take the same form, but with a little bit more advanced classical computation. So most quantum programming languages are really circuit description languages. So they're classical programming languages for building up a circuit, which is a sequential composition of linear operators. And some quantum programming languages have tried to kind of break this tradition, notably Q#. That was one of the big things with Q#, but now they've kind of gone back on that. Now they're really thinking of themselves as a circuit description language yet, because it's very hard to think about how to actually represent quantum computations in a way that isn't just a composition of gates, right? Composition of matrices. And then more recently, we've had things like the ZX calculus and diagrammatic calculi, which I believe you have heard about this morning, right? Which kind of go a little bit farther away from the circuit model towards tensor networks, right? But in the end, it's still the same sort of thing where you're composing linear operators. They're just not necessarily square unitary linear operators anymore. Okay, so how does a quantum compiler, for example, or a computer in general reason about quantum programs in one of these representations? And what in particular do we want? Yeah, sorry.
Yeah, sorry. Can I just ask, is there a way to think of this classically? Like we have classical analog, like a different way of thinking about classical computations other than just a composition of functions?
So I'm actually going to get to that in just a couple of slides. The point that I'm going to make is that I think circuits are equivalent, kind of the classical model that would be equivalent to the circuit model of quantum computations, combinatory logic. But that's not the standard model that we use. Like combinatory logic is very useful in some ways, but we still typically think of classical computations in terms of like lambda calculus. It's a little bit easier to kind of grok and understand in your head than combinatory logic. But I'll get to that in a second. Great question. Okay. So, right. ideally, we would really want a computer to really understand what a quantum program does, right? But if we're talking linear algebraic model, right, that would involve computing some sort of huge matrix. We can't actually do that, right? So what we typically do is have computers understand when two programs are equivalent. And this is using things like circuit rewrite rules. And you can do things like verify quantum programs or optimize quantum programs using these equivalences between circuits, for example. So this is an optimization taken from, this is an optimization taken from a recent paper this year, which in the end is still doing the classic thing, right, of just saying, look, we have a CX gate, a C naught gate on 2 qubits, followed by a C naught gate on 2 qubits. So we can cancel those out. It's equivalent to the edit. So this is the typical form of reasoning that we have in quantum compilers. In general, programs that manipulate and reason about quantum programs. Circuit reason, using rewrite rules, right? Writing one circuit as an equivalent circuit. And these are about 1/6 of the set of complete rewrite rules for Clifford circuits in this paper from Peter Sutherland in 2015. So that's a huge number of rewrite rules for a set of circuits that are classically simulable. Right? So we can't actually really use these rewrite rules effectively in quantum compilers because there's just too many of them. Right? Not only that, but it's not immediately obvious if we want to do something like optimize a quantum circuit, which rewrite rules we should apply. And I think Alex Kissinger probably said the exact same thing at the start of this talk, did he?
Yeah, we came to this point during the discussion. But if I may just ask you,
yeah,
isn't it a problem like chess? I mean, on a chessboard, you have at every position in the game, except at the very end, you have lots of moves and you are disposed more than Salinger has rewrite rules in his set. And there is machine learning algorithms that apparently are good at playing chess now. So could you teach them to apply these rewrite rules to your advantage? Do you think?
So some people have done that, not super successfully that I've seen.
And why? Would you point to a reason? Maybe it's not like chess. Is it maybe different?
I mean, it's possible that. So chess in particular, I think they do something slightly different because in chess you can actually analyze all of the different kind of branches of the game. And that's the way most AIs that play chess work. They actually go to a certain depth, but Go, AlphaGo does use machine learning to figure out the best move in a Go game. It's possible that in the sense of quantum computation, no one's come up with the perfect AI model that will be, really effective at optimizing quantum circuits using rewrite rules. It might just be that fact, but I'm not a machine learning guy. I'm not that interested in it. I'm interested in maybe ways that we can teach computers to reason without kind of just throwing something at a neural network, right, and figuring out that it works. Okay. I see another question.
Also, in classical computation, we have this formula of complexity of show the program to do a certain thing. That is not computable. So we still have this problem that you not always optimize certainly everything. Usually uncomputable.
Oh yeah. And in the end, this is all going to be, well, not necessarily uncomputable because most of the time quantum computation is very finite, right? It all kind of just reduces down to some sort of huge linear algebraic calculation. So that's slightly different from the classical sense. But in the end, yeah, I'm not expecting to get something that's going to, be able to find the minimal circuit over any gate set in polynomial time. Okay, so yeah, to move on, in the ZX calculus, they've kind of been pushing the field forward in certain ways by kind of reducing the number of rewrite rules because they take advantage of the extra degrees of freedom that you have when you just look at general tensor numbers instead of quantum circuits. But you still have this problem, at least in my mind, where it's not immediately obvious, where to apply a rewrite rule like this if you want to simplify a ZX diagram, for example. You still need that human ingenuity that computers can't quite figure out. So yeah, this was the point that I was going to get to about models of classical computation. And I would say that these types of models of quantum computation are analogous to combinatorial logic in classical computation, because combinatorial logic is really about point-free compositions of operators over a particular basis. So kind of like circuits or ZX calculus, right? And then reasoning in combinatorial logic is equation. Your rewrites, just like circuits. Sorry? Point free, in the sense that you don't specify what happens to it in, like when you're defining a function in combinatorial logic, you're not saying what happens to an input. You're defining it as a composition of other functions. The lambda calculus, on the other hand, is not point free. It's very much about what you do to a particular input, right? That's why it's a little bit easier, at least for me, to understand the lambda calculus than combinatorial logic, right? And then because it's not point free, reasoning is very computational. It's all about substituting values in and actually running a computation instead of this kind of equation reasoning. So what I'm wondering is there a more computational model of quantum computation than circuits? And in particular, what I'm going to be talking about today is one model that I've been working on over recent years, which is the symbolic sum over paths. And the idea behind the symbolic sum over paths is that symbolic representation of discrete paths. And a couple of highlights before I get into it. It's efficiently computable over most gate sets. So you can efficiently compute the symbolic representation, usually for circuits and channels. It's universal for qubit quantum mechanics, meaning you can represent any linear operators between even power dimensional Hilbert spaces, right? And rewriting is particularly nice because it has a directly computational interpretation. And that's because rewriting follows by reducing interfering paths, which is the first example that we look at when we study quantum computation. And this model directly encodes that idea. Right? So it ends up being highly automatable. And it's implemented in my software package Finder. So you can get that when I get it. Okay. So just a quick overview for the rest of this talk. I know I've been talking for a while already, but I'm going to talk a little bit about the representation itself, then talk about how we reason with these symbolic sums, and then finally get to applications. Okay. So the sum over paths. What is the sum over paths? Well, in the typical linear algebraic view of quantum mechanics and quantum computation, right? We think of at least a pure state of n qubits as a unit vector and see the 2 at the end, right? Simple stuff. And we can usually kind of describe or think of that as a superposition of classical states, right? These classical states X, length n bit vectors. And then computations change the state by applying unitary transformations on those states, right? So matrices in computational basis, for example. So there exists another formulation of quantum mechanics, and I don't want to talk about it too much because I'm not a physicist, and I'll probably embarrass myself. But in the 40s, I believe Richard Feynman developed the path integral formulation of quantum mechanics. And in this formulation, you don't think of the amplitude of a state as simply a complex number. It's the amplitude, the sum of the amplitudes of the paths leading to that particular state. So we can think of a quantum process like this one as sending the classical state A along a bunch of different paths, right, to B, each with their own amplitude. And in path integral formulation, these paths are equal weight, but at varied phase, I believe. Again, I'm not this. Right. So a computation really sends A to the sum of states B and C with different amplitudes. And we can think about what gates are in this kind of path integral view of quantum mechanics, right? Particularly, we can think about a gate like the Hadamard gate, which we all know the matrix of. And when we think about the Hadamard gate in the path integral view, it's really a process that sends the two classical states 0 and 1 along different paths to the 0 and 1 state, right? So we have two paths from the 0 state, one to the 0 state, one to the 1 state, right? And then two paths from the 1 state, one to the 0 state, one to the 1 state, both phase -1. And we can write this symbolically as a function of binary variables, right? Corresponding to the input and output state. And if we do that, we see that the Hadamard gate sends the classical state X to the sum indexed by this binary variable Y. The classical state Y, but the state of -1 to the XY. Right. And then we can also start to think about how we compose operations in the path integral view, right? And it's particularly intuitive in this case, because all it is composing paths, right? Composing paths through the same intermediate state. So if we do that, now we have 4 paths from the A state to the B state. And we sum over their amplitudes. And symbolically, what this is really doing is just encoding matrix multiplication in a sum, but in a sum that we can later analyze, right? So if we compose the Hadamard gate, what we end up with is a system of 4 paths indexed by binary variables y and z of a phase of -1 xy plus yz, and output state z. And because of the way this really encodes matrix multiplication, the sum of paths has historically been used in complexity proofs, right? Because if you actually encode matrix multiplication, then you can analyze and figure out the difficulty of computing an amplitude, right? Which is the difficulty of actually evaluating the sum. So this is exactly what was done in the past. And this is one particular result by Ashley Montanaro in 2017. That was really a simplification of another result by Dawson, Nielsen, and a bunch of others in 2005, which itself was a simplification of another result also in some past framework from before that. But I really like this proof because it's so simple. And specifically, right, if we write the sum of paths action, the Hadamard gate of this, paths and doubly controlled Z gate. Circuits over the Hadamard gate and doubly controlled Z gate are universal. But when we compose them, we find that the action of circuit over Hadamard and Z is this action that sends a classical state X along a bunch of paths indexed by this binary vector Y and binary vector X prime. The output state X prime, the phase of -1 to the f of x, y, x prime. And this function f in particular is degree 3, or at least degree at most 3. And then there's this old result by Aaron Feucht and Kropinski stating that computing or calculating the number of zeros of a degree 3 Boolean polynomial is sharply hard. So that immediately gives us the fact that PQP is contained in P of sharp P. Simple one-page proof. It's awesome. And then you also get some other complex implications, like if you replace the CCZ gate with the CZ gate, you get a phase that has degree at most 2. And Aaron Feucht and Kropinski also had a result saying that you can compute the number of zeros of this function in polynomial time. So that gives you a method of simulating circuits over H and CZ in polynomial time. Again, one-page thing. So I think that's super cool. But in those previous results, they weren't looking at the sum of paths as a representation of quantum computation. They were looking at it as kind of a tool for doing these proofs, right? So in order to use the sum of paths as representation of quantum computation so that we can manipulate it as a mathematical object, we need to formalize it. One way that we can formalize the sum of paths is in this one. Specifically, a balanced sum of paths is a map that takes n binary variables, right, and sends it to a set of paths indexed by some more binary variables, right, with the output state given as functions symbolic in x and y, right, and a phase that's also symbolic in x and y. And this phase we call a phase polynomial. And we can also consider unbalanced sums, right? Where instead of having a single root of norm 1, right, we can have other roots, like alpha 1, alpha 2, all raised to different polynomials. But this ends up being very difficult to work with. So it's not a great thing to do. And if you formalize the sum of paths in this way, what you actually get is a symmetrical nodal category. So what this means is that the tensor product and functional composition act in the way that we expect them to, act in the same way that they would act for linear operators. So don't worry about the definition of symmetric monoidal if you don't know it. But the point is, because the tensor product behind the sum of paths works in the way that we expect it to, we can actually use this to get a compositional model of quantum circuits. And by that, I mean we can define a model or define a representation of a quantum circuit as a sum of paths just by mapping each of our basis states to the sum of paths. And then taking the algebra homomorphism over composition and tensor product. And if we do that, it meant that the discrete path interval, the sum of the paths, is polytime computable, at least for circuits over Clifford plus RK, and other data sets too, but Clifford plus RK is particularly excellent.
By being Clifford plus your level K phase states was sufficiently high K on universal. Don't need to go very high. So your path, when you say your path being 40 times computable, that cannot mean simulation of the circuit.
Oh, no.
So what does it mean then?
So what it means is that the object, this mathematical object, which represents a particular linear operator, is polytime computable.
Oh,
So the sum is kind of left abstract. The sum isn't evaluated when we compute the sum of the paths.
so what when you say you're computing the circuit, or you're computing this function that goes into the exponential? And this minus one to be da 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 da.
Computing the representation, computing a polynomial
Yeah,
effect.
good.
Yes. So it's computing this polynomial P and these polynomials Fi.
Okay, thank you.
Okay, and then Renaud Vilmar just last year showed further that you could also extend this structure to a dagger compact category. So what that means is now sum of paths is actually universal for finite quantum mechanics. And specifically, dagger compact category is a category in which you can write string diagrams. You know anything about string diagrams? You know about the cup and the cat, which are this. Yeah, you probably saw that from Alex Kisser's talk earlier on today. But yeah. So you can define the unit, which is the cup here, eta, right? As sum over y, and your co-unit, epsilon, as this particular sum of paths. And doing that, you get a dagger compact category. You also need to define the dagger, but the dagger is pretty easy to find. So the point of all this is just to say that this is a universal representation. Any linear operator between even power complex vector space can be represented in this way. That's cool. And then some examples, right? You can do the partial trace. You can write the partial trace of a linear operator in the sum over paths framework. And that's just using the standard string diagram. So this is just a textual representation of the string diagram, because I didn't have time to tick seed the string diagram. And same thing with measurement. So now that we have a representation of quantum computations that is universal, right, in the sense that we can represent circuits, channels, whatever, what can we do with this representation? Why is this representation actually useful to use? And the use comes out of the ability to reason about these sums. So the key thing, right, is that the sum of paths representation really syntactically encodes matrix multiplication in a way that we can analyze the matrix multiplication. Right? So the sum of paths representation of the identity matrix just takes x and maps to x. The sum of paths representation of the HH matrix, which is the same thing as the identity matrix, right? Maps x to this sum over 4 different paths in x, y, y, and z. And we could evaluate the sum, but that would be exponential time, right? But the nice thing is that now what we can do is we can actually simplify the sum without evaluating. So to see how we can simplify the sum without evaluating it, let's take a look at this HH example, the simplest example of interference in quantum in standard quantum circuits. So to see how this interferes, we can expand out the sum. So starting with x on the left here, we can expand it by the values of y. Right? So on the path with y is equal to 0, we get this particular sum, that's the output. And the path with y is equal to 1, we get this sum, that's the output. With an additional phase of -1 to the x. If we further expand out the paths indexed by the values of z, we get this system of paths, right? With these two paths leading from x to 0, with a phase difference of -1 to the x, and two paths from x to 1, a phase difference of -1 to not x. And it's not easy to see where the interference occurs here, because we summed over 0 and 1. But what we can do instead is sum over x and not x. Sum the values of z over x and not x. So now we get this system of paths with recognizable interference patterns. In particular, the two paths from x to x constructively interfere. And the two paths from x to not x destructively interfere. So what that means is that only the paths ending in x survive. The paths ending in not x destructively interfere, cancel out. Right? So we can rewrite the sum as just x. And in general, right, we can realize the fact that x doesn't matter. The value of x doesn't actually matter. We can replace x with any Boolean expression, p. So what we end up with is this generalization, right, where we have sum indexed by two binary variables y and z with a phase of -1 to the zy plus yp for a Boolean expression p. And this output state that only depends on z. We can actually just remove that sum and substitute z with p and multiply it by 2. And if we play this game and look at some other circuits that exhibit this kind of interference, we can actually come up with a system of rewrites that actually do this kind of analysis of the interference in our quantum circuits. And these are 5 particular rewrites for some of the paths. And these first 3, E, H, and omega, turn out to be complete for Clifford circuits, meaning any equality that holds between two sum of paths of Clifford circuits is witnessed by these 3 rewrites. On the other hand, if we add in this flow rule and this A rule, we get a system of rewrite rules that's complete for linear operators. But the only problem is with the A rule, this actually takes balanced sums to unbalanced sums. So that's kind of an open question, or at least it was an open question until just recently, last month, when Renaud Jomar came up with a system of rewrite rules that keeps balanced sums in the balance frame. So that's super cool, but I'm not going to talk about it because I have the right state. So to just explain how these rewrite rules actually work when we're reasoning about circuits, let's take a look at a quick example. So what if we want to figure out what computation this circuit actually performs? You might recognize the circuit, but if not, we can write out its sum of paths action and then use these rewrite rules to simplify it. So this is the sum of paths action of this circuit here. And if we rearrange the phase polynomial a little bit, we see that it has this structure where we have y2, y1, y2, x3 plus x1, x2. So what that's saying is that y2 is really equal to x3 plus x1, x2. So we can apply the H rewrote rule to simplify the output. And we just get that the output of the circuit is x1, x2, and then x3 whole plus x1 times x2. So it's the Toffoli gate. Simple. It's one rewrite, completely symbolic. Okay. So applications. So what can we actually do with these rewrites in this representation? When I first started working on this, I mean, the main reason was to be able to verify quantum circuits. I was interested in verifying quantum circuits. And the reason is that there's this high degree of uncertainty about the resource estimates done about quantum algorithms. So as part of this project years ago, this IRPA QCS project, developing quantum compilers and actually getting resource estimates for quantum algorithms, like figuring out how many gates, what the depth is, that sort of stuff. And part of the reason this program sunk was because there were 4 different teams. They all gave completely different resource estimates. And the government, the US government, because it was an IRPA project, had no idea which team was correct. And they asked us to verify the results of our resource estimates, and we could. None of the teams could, right? Because these circuits are so huge, we had no way of actually knowing that the resource estimates were correct. And then kind of a little bit more practically, there are also bugs in quantum circuit optimization papers, including my own quantum circuit optimization papers. We found bugs in my papers, nothing like that. So I wanted to be able to verify that those circuits are correct. So when I first started working on this, the main application was this verification. And at the time, this was 2018, it was able to verify some of the largest circuits that have been verified in the literature. So this is a table taken from that 2018 paper. And it was able to verify some circuits on up to 200 qubits in just 5 seconds. So this Toffoli circuit, for example, implementation of 100 control Toffoli of 197 qubits. Took just 5 seconds using purely this automated rewriting. So that was really cool and kind of exciting. And since then, this tool has been used to verify the correctness of circuits in a number of academic papers and also find bugs in some of these. So that's kind of cool. But since then, also done some experiments verifying things like T-gate, teleportation channel, right? And also some measurements assisted on computation circuits for up to 128 qubits. That was a fun one. Because for verifying the channels, you have to double, right, the size of the system. So it's actually quite effective. But this is my favorite example that I always like talking about. I think Alex Kistner talked about exactly this circuit this morning.
Yes, it did.
Yeah. Okay. So.
Can I, sorry.
Yeah.
Maybe just eager to speak about it. Would it be possible to post-process the previous example for a bit?
Post-process?
Yeah. So, I mean, you said rewrite. So, using purely automated rewrite. I mean, earlier in the talk, you showed us the rewrite rules for even Clifford systems and then the rewrite rules in DZX calculus, and then there was a problem you can apply them forward and backward, and you don't know what helps you and what hurts you. You seem to be getting around it when you say purely automated rewriting in seconds. So it seems you know which rewrite rules give you an advantage.
Yeah. So that's a great question. Thank you. The reason is these rewrite rules all reduce the number of variables that you're summing over. if you just, yeah, if you use this in a purely straightforward manner, where you're just reducing the number of variables that you sum over, it's an extremely simple, algorithm, right? Because all you're doing is using these in one direction, forward direction, and you're able to do some really insane things.
Okay, okay, so that is a huge clarification for me. And so let me just kind of conjecture. So you end up with a polynomial, with a, with a polynomial function for your exponent, and somehow there's this normal form where you always have the same summation, and basically, so your verification amounts to comparing these polynomial functions in the exponents of the phase.
Yeah, so what it,
Maybe you say it in your words. What do you do when you verify a circuit?
so it's really just applying these, it's a pattern matching problem. Matching your particular polynomial with something of this form. It's actually very simple to match with something of this form. All you need to do is check that, well, you look at a particular variable, take the quotient of that polynomial divided by that variable, and check whether that polynomial is Boolean. Okay. And if it is, then you can apply this rubric. It's very simple. I can show the code too. So hopefully going to show some demonstrations in my code.
Okay, be happy to see, but I think it gives me an idea what I'm thinking.
Right. So this hidden shift circuit with these Meyer-Arlen functions has been used to benchmark a number of simulation methods, including the one that Alex Kissinger talked about this morning. And the cool thing is with this method, you can really just crush this particular simulation example. The 2019 paper by Sylvia Rabi and a bunch of other people simulated this particular circuit in 28 hours using their methods. It's 2019. It takes 5 seconds by doing this automated rewriting. And then I just ran it on the 1400 T-gate example that I saw was in Alex Kissinger's paper this morning. And does it in about 1 minute using nothing but automated rewriting. And I'm just going to run that example right now while I finish my topic. This is on a tablet computer, right? Okay.
How long does it take on the graphical rewrite?
What was that?
How long does it take the graphical rewrite?
I don't know. I just looked at the paper this morning, saw it was the 1400 T-gate example, and I ran it. You would know better. You saw Alex Kissinger's talk. Okay. So last thing I'm going to talk about, because it's something that I've been working on recently with my collaborators, Owen Bennett Gibbs and Julian Ross, is applications to synthesis of quantum circuits and optimization. So, oh yeah, and we're presenting this at QPL later this month. So over Clifford circuits, path sums have this particular form, right? And this is a well-known form, actually. It's been known for years and years. It's called the affine form, or some people use different terminology for it. But basically, a circuit over HC on S maps classical state X to this particular sum, where the phase is given by I raised to the linear polynomial and -1 raised to the quadratic polynomial. What was that? Yep. Sir? Yeah, exactly. It's a standard form, right? And this is exactly what you get when you compute the sum of paths. over this particular data set. And now the neat thing is that you can actually get to the normal form of this representation, the affine normal form, or I think it's also known by some other names, right? And you can get to this normal form just by applying those same redirections, this E, H, and a. And you can get to this normal form in polynomial time. So as a corollary, you immediately get the fact that you can simulate Clifford circuits efficiently. But the cool thing, when we write a Clifford operator in this normal form, then it immediately decomposes into a sequence of 5 operators, right? One applying all the phases dependent on the input x. One applying a linear reversible function to prepare this Rx, and this Rx is just the cross terms of this quadratic function Q. And then one applying the layer of pattern or gates, another applying this affine reversible function to prepare the output function, this x1. And then finally, phase computation to apply the phases depending on y. When you decompose the normal form this way, you immediately get this 8-stage circuit, which is previously has been arrived at using this Bruhat deconstruction of the Clifford group, right? But this is a purely constructive proof. It's a proof that actually has a constructive polynomial time algorithm to generate this 8-stage circuit. And it's really trivial. Again, in our paper, it's only 1 page. And this is what the circuit looks like. I'm just blasting through this actually. Someone gets the okay. So synthesizing more general circuits. We also in this paper looked at the question of whether we can synthesize not just Clifford path sums, Clifford sums over paths, but non-Clifford ones as well. And the neat thing is you can do it again using this idea of redirections. In particular, we can kind of invert the sum of paths actions of a set of basis gates. And that gives us a system of rewrite rules that have actions, or if you're a fan of logic, technically proof. We're reducing a particular sum of paths to the identity using a system of gates. So if you multiply control x state, for example, just uncomputes the product of the input register. Multiply controlled theta phase state uncomputes a particular phase. Right? And the Hadamard gate uncomputes this system of paths. So you can synthesize by applying these rewrite rules to reduce a sum of paths expression to the identity. And the first example that we tried on this was using it to synthesize the quantum Fourier transform. And the quantum Fourier transform, if we write it as a matrix, it's this ugly matrix here. But if we write it as sum of paths, it has this very elegant description, right? Where this particular product is as integers. But still very nice looking description. And if we give our program, for example, this description of the QFT, we can actually synthesize exactly the classic QFT circuit, completely automatic. And this is how. This is the derivation of the QFT circuit using these rewrites. I'm not going to go into this in too much depth, I think, but you can see, right? You have the Hadamard gate, then the control S, and the control T. Another Hadamard gate, control S, and the final Hadamard gate.
23 again. Let me just, my question is, how does your algorithm know that the first thing to apply is stage 1?
Yeah.
And earlier you said something about the visibility of polynomial, Is it? Please say it again. You just kind of, in the polynomial, somehow you seem to be, the polynomial seems to know which rule can be applied next. Can you maybe say it again explicitly so that I can remember it better?
So again, the idea is really just about finding one of these variables that you can remove. Finding a variable that you can remove so that you simplify it.
Yes.
Yeah.
So you say it's automated. So what property of the polynomial up there is checked?
It's not a property of the polynomial itself, it's property of the sum. So we're trying to, at each stage, remove one of the variables that we're summing over. And we can remove one of the variables that we're summing over by matching the polynomial. And in this particular case, we also need to match with something in the output cat to be able to apply a rewrite rule that will eliminate that variable. But the point is, as long as we're eliminating variables, we're making progress. There's this extremely natural notion of progress, where it corresponds to the number of variables that we still have.
We don't want to hold up this. I want to come back to this later. Yeah, there's another question.
Oh, yeah.
Do you understand correctly that you give some rules about the simple like H1 convergence and so on, and this takes your complicated function QFT and just decomposes it with this gates?
Yeah, exactly.
And what happens if you have two different decompositions for the same circuit? So this is random?
I mean, it could be random. The way I have it coded, it's not random. It tries to find a particular rule first, and then goes to the next rule.
So
But it's just a pattern matching thing. I can even show you the code. It's just matching on a particular pattern and then applying that rule if the pattern matches.
QFT hard to implement for power 2, right?
Yeah.
Is that all your that having the number of units?
Yeah, so I don't know exactly what it would do for the non-power of 2 QFT. But that's an interesting one. I want to try that at some point. Oh, so if that's what you mean by the power of 2, like the number of, if it's an even number of qubits or not, yeah, then this is fine. It's odd number of qubits, synthesizes it just fine.
No, it would be like, so this is a dot, this is 2.
Yeah.
Okay.
Yeah. Okay, that's where, yeah.
Sorry, what are the limitations of this? Like it's right. Like your verification time of 5 seconds. What would what would some of the limitations be?
So I mean, I pretended like it always works perfectly. It doesn't, right? It works particularly well if the circuit has a relatively simple kind of interference structure. So typically stuff that involves classical computation in superposition has this kind of structure. That's why it's so simple with the hidden shift example. It's just classical computation in superposition. And it ends up being a single output state. So that's the other situation. This method doesn't work very well. When you have a lot of states with non-zero amplitude, and you want to find one that has, for example, a particularly high amplitude. It's not very good at that. It's very discrete. So it's good at finding, simplifying, circuits that end up with just one peak in the output, not kind of one peak and then lots of smaller peaks. Okay, but I do think I'm out of time, so maybe I'll just leave it at that for now and go back to the definition. Just see that. Oh yeah, okay. It did manage to compute the hidden shift in this case for something like 10,000 gates, 1,400 T gates. Probably did this in about a minute. Okay, and I'll leave it there because I'm out of time.
I'm quite interested in this fact that the Clifford circuit produces this Gaussian type of things, the quadratic plus the linear term. Is it true the other way around, that if you have a Gaussian phase, then this Clifford circuit?
Short answer, yes. I think. Long answer, I think there may be a couple of caveats. If you have some of the paths with this representation where the phase has this kind of Gaussian type thing, you can end up in a situation if the polynomial is of certain forms where it's not actually unitary. So then you can't synthesize, of course, a unitary Clifford for it. Yeah, but even if it's not unitary, you can still synthesize a Clifford circuit in some cases that uses ancillas also, as long as the number of qubits at the end of the circuit is greater than the number of qubits in the beginning of the circuit. You can add in ancillas and you'll still be able to synthesize a unitary Clifford circuit, just having ancillas at the beginning.
So does that imply that non-interacting quantum field theories are Clifford circuits?
Interesting. Is that a known thing?
No, not to me. Quantum field theory. I mean, so usually like Gaussian path integrals are easy to do, like non-interacting particles. And this is also like a path integral. And somehow like also Gaussian things are easy. That would be Clifford circuit. So if it isn't just I see two closely related patterns, so it's a connection.
Like one fermion will go on match gates and I don't know.
I see another connection. So you mentioned marijuana fermions.
I mentioned non-interacting fermion and like and non-interacting boson things have like match gates and like renewable sub-theories are like one of the I forget what the
Fermion equals match gates.
Right.
Bosons, I think this is something that Polina mentioned in our talk. So Gaussian states and Gaussian operations are efficiently simulable. And that is kind of analogous to the Gaussian middle theorem. So for the Gaussian stuff, what you would be tracking is the covariance matrix. And the kind of stabilizer states are kind of, in a way, degenerate Gaussian states that are elongated in one direction. And the information that you're tracking is that direction. So, I mean, you can just kind of clarify that at home. Like that is, yeah, I think at some level, I would agree to what you said, that there's a connection. So there's kind of this covariance matrix tracking, stabilizer formatted, and very similar things. I don't know, what do you know? You presented this briefly, but would you want to comment on?
I think I have nothing to add. I mean, I know that the stabilizer states can be actually represented by Gaussian functions, but it also does not bring us closer apart from having the same pattern. So I'm not sure that they have completely understood Mitchell's question.
Like, so usually if I write down a quantum field theory, I write down some path integral.
Yes.
And then Gaussian path integrals are particularly easy to work with,
Yes.
like non-interactive ones. And then if you add like interactions, things become complicated. And it's kind of the same story here. So if you have a Gaussian thing, then it's corresponds
Yes,
to
yes, yes. But
with
what
a
is
circuit.
the question?
More or less, like, is it so? Is there like, can you extend it to, like, can you draw this analogy between quantum field theories and circuits?
Can you draw this analogy between quantum field theory and quantum computation with continuous variables? Because if yes, then the answer to the entire question is also yes.
Yeah.
So another way to ask the same question would be, can one use your symbolic formalism for continuous variable computation?
I want to say no. But I mean, I would be interested to look at that at some point in the future. And to me, it's a very discrete formalism. This one, the rewrite rules are really based around the fact that you have these discrete sums where you have, you know, for a particular variable that you're summing over two options. And then you just have this simple kind of either constructive, completely constructive on the one hand and completely destructive on the other hand, interference that allows you to simplify the sum. I would imagine it's kind of a different story.
I could imagine that it would not immediately lead to an algorithm which can be automated and used for these tasks, but maybe if one tries to think in the same way that you do about quantum circuits, about continuous variable computation, one might arrive at the standard path integrals. This might be useful to prove something.
Can I just add to that? I mean, just so that we're not immediately confident. I mean, just something that, I mean, you had this point in your presentation where you talked about the degree in this theorem, whatever the names were from 1984, whatever it was. So that kind of degree 3 is the threshold. Yeah. If you're below 3, then you're officially simulable, and 3 makes things off. And I mean, so in continuous variable quantum computation before KLM came up, the preferred way of getting to universality, I mean, theoretical, I mean, not practical, but theoretical way before KLM would be a current nonlinearity.
Yes.
So again, the degree of interaction comes up as a critical thing. Yeah, so I think there's fitting elements on either side.
It's like a natural question: if you feed your machine a quartic term, like thing which has like quadratic and then a quartic thing, like what will it split out?
I mean, so it depends. It depends what the end result is. Like, for example, on I mean, something that would give you a quartic term, at least in this model, would be like a 4-qubit Z gate, right? Like a 3-controlled Z gate. That gives you a quartic term. If you have that followed by another, 4-qubit Z gate, it would just cancel them out. Yeah. I'm not sure if that answers your question. But basically, yeah, I mean, in the end, if you have high degree terms in your polynomial, rewriting can kind of expand the degree of those terms even further. So that's why it actually maintains classically simulable for degree 2 and less, because it doesn't increase, when you do the rewriting, it doesn't increase the degree of the polynomial if the polynomial starts at degree 2. But once it starts at higher degree, rewriting ends up increasing the degree even further.
Yeah, it's kind of like in critical theories, when you have like this 40 terms in lambda to the 4th degree, you go to a critical point, you have correlations on all length scales. So your renormalization group will generate all terms.
Interesting. Huh. Yeah, see, the weird thing is I'm a computer scientist. So all of this stuff like arrives out of completely kind of what I think of it as discrete classical thinking. But it has all these analogies, I guess, to the campus. Yeah.
Yeah, so just maybe your feedback, some questions that Robert was asking earlier. So I've kind of always seen the success of the ZX calculuses. I mean, I kind of give up this notion of unitary, right? Maybe I have more flexible rewrite rules because now I decompose my circuit to just a fraction of a bunch of isometries rather than a fraction of unitaries.
Yeah.
I don't know. So I guess, is there some way in which your method is more flexible than forcing that my rewrite rules take unitaries to be
So can you say the last part of the question again? Sorry.
Yeah, so is there any way in which your method here is just more flexible in the sense that what it's describing is something more general than just unitary transformations?
Yes, I think there is a natural notion of that because so that just like with the classic path integral, one of the things that's very hard to read from some of paths representation is whether or not it corresponds to a unitary transformation. So in some sense, if you do rewriting, it's not immediately obvious anymore that it actually corresponds to a unitary transformation. So it kind of like escapes the realm of unitarity in that sense. But I think it's a slightly different kind of question than the ZX calculus, because the ZX calculus, like you mentioned, gets that extra power from leaving the unitarity kind of realm. This gets the power, I think, of from the fact that you have a direction to actually go when you're rewriting, rather than just the fact that you're like leaving the unitary sphere. Or sorry. That's a good question. I don't know. On this 8, it's kind of this, to a certain extent, okay. It's kind of a silly distinction to make, right? Because it's an 8-stage circuit. If you're talking about specifically, that one type of gate in each stage, on whether it's a valuable distinction to actually make. I think the more valuable distinction to make is the fact that you only need a single layer of Hadamard gates in the center of the circuit. And then the rest of the stages, you can combine the X gate and the C naught gate like into one stage. That's what the Dmitry Maslov and Martin Roppler paper did. So they actually said it was a 7-stage circuit, which isn't completely true because they're combining X gates and C naught gates in the same stage. So they actually end up with a 9-stage circuit, right? But it's all with this kind of stuff. It's splitting hairs to a certain extent. I think the interesting part is the fact that you can do it with a single layer of Hadamard gates, which is obviously provably minimal.
So Alex Kissinger also talked about the hit chip problem this morning. And he got a question from David Gossett. And David Gossett asked, your simulation method seems to be working particularly well on the same shift problem. Have you identified the structural reason why this is so? And I think he wave text, this is my recollection of his answer. So now you have done something more analytical, it seems. So can you answer the question? Do you know from your simulation whether there's a structural reason that the shift problem is suited to your simulation methods?
I have ideas on why that's the case. It's something that I've meant to look at. I just never really got around to it because it's an extremely interesting question, and yeah, it's something that I want to look at, and I think there is a path to figuring out how, why it's so efficient for these particular methods. I don't know right now what that reason is.
When you learn, so.
All right.
Okay, we always get anxious.
I could do that all day.
I apologize.
Sorry, I was just asking whether there were questions in the chat.
Good.
Thanks,
Yeah, that's